So in this video, I am going to explain upsampler and upsampling process, graphical illustration and mathematical illustration. So now upsampler means which is improving or increasing the sampling rate of the given input signal. So if you give x of n as an input to the upsampler, so then it gives the output y of n. So that is equal to x of n by L. That means x of n by L means here. So here sampling rate is increased. If x of n into L, that means sampling rate is decreased. Okay. Now y of n is equal to x of n by L or x of n by I. You may use I also here. Now here y of n is equal to x of n by L. Now here that means x of n is given like this: x of 0, x of 1, x of 2, x of 3, x of 4 and so on, right? So to determine or to increase the sampling rate of the particular signal, so in between these samples here use the zeros, right? Use the zeros, and then by adding these zeros in between the particular successive known samples, so here sampling rate is increased. So now x of n by L means actually L minus 1 zeros are added between the samples. So x of n by I means I minus 1 zeros are added here. Okay. So now so consider here example. So x of n is 2, 4, 6, 8. At x n is equal to 0, the amplitude value is 6. Okay. Now find zero interpolation, step interpolation, linear interpolation. So now here you just observe what is here zero, step, linear interpolation techniques, right? So now here zero interpolation means you just add the zeros in between the particular successive samples. Step interpolation means here here we just add the value in between the two successive samples. So that value is nothing but related to the previous value, right? Previous sample value. Okay, right. So here linear interpolation means you just add the values here also in between the successive samples that follows the linearity here. Okay, so see here in this example 2, 4, 6, 8. So if you want to find out x of n by 2 here, if I take zero interpolation technique, so now here in between here samples here add the zeros, right? So I minus 1 zeros means here I is the 2, 2 minus 1 means 1, so 1 0, add the 1 0 between the two successive samples. So right, 2 comma 0 comma 4 comma 0 comma 6 comma 0 comma 8 comma 0. In this way you can improve the or you can increase the sampling rate. Now coming to the step interpolation. So step interpolation means here, so now here add here I minus 1 values here also in between successive samples. So here that is related to the previous sample. That means here 2 comma 4 in between, instead of using 0 here use the 2, that means this value. Now here also take 4, here also take 6, here also take 8, and the same value like that, step nature, that means same value. Now here coming to the linear interpolation. So now 2, 4, 6, 8 is there. In between 2, 4, so increase the number value. That means 2. After 2 you can get the 3. That's why here use 3. Next in between 4, 6. What is the next value of 4? 5. In between 6, 8. So use the next value of 6. What is that? 7. So like that you just interpolate values with the nature, linearity nature. Okay, right. So okay, this is nothing but zero step linear interpolation techniques. Usually we are adding zeros. Okay, I minus 1 zeros. Now so here do the problem here. Let x of n 2, 2, 5 and sketch x of 2n and then x of n by 3 using zero interpolation, and then step interpolation, linear interpolation. Sketch the x of n by 3 also and find the x of n by 3 value. Okay, so do it one as an exercise. Okay, right. Now coming to the illustration here, interpolation by a factor I. So here the block diagram is nothing but upsampler and low pass filter. So see in the case of decimation, what is the block diagram? Filter and downsampler. Okay, right. Here see the block diagram. Upsampler, filter. That means this is the just in different process. That means first of all use the here there filter and then there use the downsampler, but now use the upsampling action first, later use the filtering action. So here remember this one. So first here an increase in the sampling rate by an integer factor of I can be accomplished by interpolating I minus 1 new samples between the successive values of the signal. Okay, as I said earlier. So okay, that is the story. So now here coming to the block diagram. So this is the block diagram. So first of all use the upsampling action, then use the low pass filtering action, then you can get the what is that. So here sampling rate increment. Okay, now so here if V of m, which denotes a sequence with a rate I into f of x, which is obtained from x of n by adding I minus 1 zeros between the successive values of x of n. Now we can represent that one as V of m is equal to x of m by I, where m is the 0 plus or minus I plus or minus 2a and so on, otherwise it is 0. And then take the z transform here, that the z transform is nothing but V of m into z power minus m summation. Now what is the here V of m, so this is x of m by I. Use this one here x of m by I and then assign m by I as a one new variable and then convert, and then if you modify this particular here like this, if you simplify like this, you can get x of z power I like this. That means, right, so V of z is equal to summation x of m z power minus m I. So then this is nothing but z power I whole power minus m. That's why here in the place of z, here is a z of I, z power I. So now this is equal to x of z power I. So now here V of z is nothing but here if you place e power j omega y like that, is simply I am taking here omega y. So now V of omega y is equal to, so here actually it is e power j omega y, but that is denoted as here omega y. Okay, x of omega y into I, here also e power j omega then into I. That's why here omega y is equal to omega y into I. Okay, now omega y represents the frequency variable. So relative to the new sampling rate fi. So omega y is equal to 2 pi f by fi. So now the relationship between the sampling rates fi is equal to I fx. Now omega y is equal to omega x by I. Okay, right. Now coming to the here graphical illustration. So now here consider the spectra of x of n and then take the V of omega y like this, right? So upsampling. Now here take one filter with the bandwidth what is that pi by I, so 2 pi by I. So now here after passing this particular signal via this filter, so now so filter frequency components, right, filter what is that lock the certain frequency components and does not allow the other higher frequency components. Now so it is it looks like this one, right? So now here this is nothing but the output spectra. So now here from this we can easily observe that the sampling rate is increased. Okay, right? So the scale factor C is selected so that the output y of m is equal to x of m I. Now at m is equal to 0, if you observe y of 0 is equal to C by I into x of 0. If you simplify this one, you can get the C by I into x of 0. So if C is I, then that is a desired normalization factor, then y of 0 is equal to x of 0. It's okay. Now here this is nothing but graphical illustration and what is that? Mathematical illustration. In this we just focus on particular spectra of each signal and also here mathematical analysis. Okay, thank you.